In this video, we'll be reviewing variance and standard deviation. Now, we've already gone over expected value in previous videos, but I'm just going to do a quick recap on the expected value of this distribution here in the table, which is essentially the mean. Now, in order to find the expected value, or mu, okay, so just be aware that, if you see this mu, it represents the expected value, or the mean. We just need to find the sum of the values multiplied by its probability. So I've got my values 0, 1, 2, 3, and 4, their respective probabilities here, and then I've just drawn up a third column, which is just my x times p of x, and I've just done those multiplications as such. So I've done 0 times 0.2 to give me 0, 1 times 0.1 to give me 1, 2 times 0.3 to give me 0.6, 3 times 0.25 to give me 0.75, and 4 times 0.15 to give me 0.6. I then need to add them all up. I'm then expected to add them all up, and that gives me an answer of 2.05. So my expected value for this distribution is 2.05. Now, the expected value, or the mean of random variables, is just a measure of location or central tendency, and it's very important and gives us so much information about my values. But it's also really important to review the spread of these values and how far away they are or how close they are to the mean. And this is where variance and standard deviation comes into play. So variance, informally, it just means how far a set of numbers are spread out from the average value. And in order to find the variance, I'll first need to start by taking the difference of each value from the mean. Now, we call this difference the deviation. I then square the deviation simply just to make it positive, and it's just easier for us to use. Then, as we did with the expected value, I then take the weighted mean of this squared deviation, and I'm left with the variance x is equal to the sum of, so I'm using the sigma notation again, of the probability times it by x minus mu all squared, because I'm finding the weighted mean of this squared deviation. So based on that example, let's now determine the variance of these set of values. Okay, so the first step was I needed to find the difference of the value from the mean. So that's just simply 0 take away 2.05, then 1 take away 2.05, then 2 take away 2.05, 3 take away 2.05, and 4 take away 2.05, leaving me with those values. I'm then going to find the square of this difference, and that simply leaves me with those values there in that next column. Then to find the weighted mean of this squared deviation, I then need to multiply the probability with that squared difference. Okay, and again, creating another column here, I get those outcomes. Okay, so that's just simply 0.2 times 4.2025 to give me 0.8405, 0.1 times 1.1025 to give me 0.11025, and so on. Okay, coming back to the formula to find the variance there, I'm then going to add all of these values here in the last column, and that gives me 1.7475, or is just 1.75 to 2 decimal places. Now, I like to do it in table form. I like to really break it up, but there is actually another formula for variance, and some may think, it's even simpler and requires less working out. So let's have a look at it. And it's really important to be familiar with both, just so that you understand it. Now, remember, in both cases, I still need to find the expected value. So you still need to do this step here regardless. I still need to find x times p of x, add them all up to get my expected value. But seeing that was another part of the question, we had already done that. But just so you know, depending on whichever formula we go ahead and use, I will still need this column here. Now, I didn't put that column in only because in this example, I already know what the expected value is. So I'm just going to get straight into it. Now, the formula reads as such. So it's simply finding the sum of x squared times its probability minus mu squared. So now I've got x, p of x. X squared is very simple to find. So it's just the square of its value. So 0 times 0, 1 times 1, 2 times 2, 3 times 3, and 4 times 4. Okay, straightforward. And then I'm going to multiply the value squared by p of x. So in this case, it's 0 times 0.2. Here it's 1 times 0.1. Here it's 4 times 0.3, then 9 times 0.25, then 16 times 0.15. I'm then going to add all of these values together to give me that, and that gives me 5.95. Okay, now I can also write it like this, it's e of x squared, my weighted mean of my values x being squared minus mu squared. So this part here again is simply 5.95, and then mu, which is 2.05, so square it, and that gives me 1.7475, which is great. It's exactly like what we had before. Or to 2 decimal places is 1.75. Alright, so let's get on to standard deviation. Well, standard deviation is simply defined as the square root of the variance. So it's usually denoted by sigma, and so that just means the standard deviation is equal to the square root there of the variance, or you can write it as sigma squared is equal to variance x. In some ways, the standard deviation is actually more tangible than variance, since it is the same unit as our values x. So for example, if x is a random variable measuring lengths in meters, then the standard deviation is also in meters, while the variance would be in square meters. What is important to understand in relative terms is a small standard deviation, or the variance, means that the distribution of the random variables is narrowly concentrated around the mean. Also, a large standard deviation, or the variance, means that the distribution is spread out, with some chance of observing values at some distance from the mean. Alright, let's have a look at an example. Suppose an individual plays a gambling game where it is possible to lose $1, break even, win $3, or win $5 each time she plays. The probability for each outcome is provided by the following table. Determine the expected outcome, variance, and standard deviation. Okay, so what we've got here is our outcomes represent our values, and we've got their respective probabilities there. So there is a 0.3 chance in her losing $1, there is a 0.4 chance in breaking even, 0.2 chance of gaining $3, and 0.1 chance of winning $5. Okay, let's determine the expected outcome. Now the formula for the expected outcome is the sum of my values multiplied by its probability. So I'm going to do minus 1 times 0.3 plus 0 times 0.4 plus 3 times 0.2 plus 5 times 0.1. And that gives me minus 0.3 plus 0.6 plus 0.5, leaving me with 0.8. So this means the player can be expected to win about 80 cents. Okay, so that's how we interpret that information there. And therefore we also say that the odds are in their favor. Now in this particular example, it didn't ask us to explain our expected value. I've just done that, something extra in case, the question does tell you, and then interpret the solution. So again, it's positive, so therefore it's a gain. So the odds are in her favor, and this 0.8 obviously goes back to, our values here, and it's 80 cents. Okay, let's now determine the variance and the standard deviation. So for variance, I've chosen this formula. Again, it doesn't matter which one you use. So I've chosen the one where we are going to square our value, multiply it by its probability minus mu squared. Now we already know mu is 0.8. We just found it. It was our expected value. I've got 2 rows here, which is what was given to me. And then I've added an extra 2 rows, so x squared and x squared times p of x. So obviously x squared is 1. And x squared, which is 1 times p of x, so times 0.3 is 0.3. I'm then going to square 0, and that's obviously just 0, and then 0 times 0.4 is 0. Squaring 3 gives me 9, and then 9 times 0.2 is 1.8. I'm then squaring 5, and that's obviously 25, and then 25 times 0.1 is 2.5. And so now to determine the variance, I'm then going to add all of these values here. So the 0.3 plus 0 plus 1.8 plus 2.5. And I'm going to take away mu squared. So that leaves me with 3.96. And now for the standard deviation, I just need to find the square root of 3.96, and that's just 1.99 to 2 decimal places. Alright, let's have a look at another example. Let's consider the following 4 discrete distributions. I then want to confirm that each graph represents a probability function. How can I confirm that it's a probability function? Well, I know each one of my probabilities here is greater than 0. So that's great. I can see each one of these are greater than 0. And I can also determine that the sum of each of these probabilities added together give me 1. Have a look here. 0.1 plus 0.1 plus another 0.1 is 0.3. Plus 0.2 is 0.5. Plus another 0.1 is 0.6. Plus another 0.2, 0.8, plus another 0.2 is 1. And if you were to add each one of these up together, for each distribution, you get 1. So this is how I can show that it is a probability function. Okay, now I want to calculate the value of the mean in each of the cases. We're having a look at case A. In order to find the mean, or the expected value, I simply need to multiply the value by its probability. So that's just going to be 1 times 0.1 plus 2 times 0.1 plus 3 times 0.1 plus 4 times 0.2. And then these are zeros. Then plus 8 times 0.1 plus 9 times 0.2 and plus 10 times 0.2. Add them all up together and I get 6. Now on to B. Same thing, to find mu, I'm just going to do my value 1 times 0.1 plus my value 2 times 0.3 plus 3 times 0.1. These are all zeros plus 10 times 0.5, and that also gives me a mean of 6. This one here simply going to be 5 times 0.2 plus 6 times 0.6 plus 7 times 0.2, also giving me 6. And finally, I've got 2 times 0.1 plus 4 times 0.2 plus 6 times 0.3 plus 8 times 0.4. And that also gives me 6. Now what this means is each one of these discrete distributions has a mean of 6. But they don't look like they're spread the same. And so this is where the outcomes of the variation and standard deviation are going to vary. Okay, so even though they may have the same average, the same mean, doesn't mean they have the same spread. So let's look into determining the variance and therefore then the standard deviation of each. For A, now I know that the mean is 6. Okay, I've put it here in table form. These are just the outcomes from the graph into table form. And I've put a column for x squared, and that's really straightforward here. Each one of these values squared. Okay, from 1 through to 10. And then I've just done x squared multiplied by its probability. Okay, and again, this probability here was taken straight from the graph. So if I have a look at value 1, the probability is 0.1. For value 2, the probability is 0.1. For value 3, the probability is 0.1. For value 4, the value is 0.2. For value 5, 6, and 7, there's 0. Value 8, 0.1. Value 9, 0.2, and value 10 is 0.2. Okay, I've then multiplied each one of these and so on, and then added them up. Okay, and I get 47.2, and I get 47.2. Now to find the variance, I'm going to have to plug that into the formula. Now 47.2 is this section here. And so that leaves me with 47.2 minus 6 squared, which is 11.2. And then for the standard deviation, it's just the square root of 11.2, and it's 3.35. Question B, same thing. I've obviously squared the value of all my x values here. Again, this column here has changed according to what my distribution is in graph B. And then I've just done the same thing. Okay, those values, they're multiplied by each other, and then I found the total sum. So knowing that the mean is 6, this is the formula. 52.2 represents this part here of the equation. So then I'm left with 52.02 minus 6 squared is 16.2. So the standard deviation is 4.02. Looking at it, my values are not that spread out. So I should get a standard deviation less than what I found before. As you can see here, I've got my score spread from 1 through to 10. Okay, and I got a spread, my standard deviation of 4.02. Let's have a look now and see what I'm going to get in the next one where my values are much closer together. Okay, again, I'm going to multiply my p of x by my x squared in each one of these columns, and you can go ahead and check those. And my total is 36.4. Knowing that my mu is 6, and this is my formula, sub that in, I get 36.4 minus 6 squared, and I get 0.4. Okay, and for the standard deviation is 0.63. As you can tell, very small, so that, which means that, you know, my values are then closer to its mean. All right, and for question D, same thing. My x squared times my px all total to 40. So subbing that into the equation, I get 40 minus 6 squared, which is 4. And for the standard deviation, it's 2. As you can see, my scores are spread between 2 and 8. Okay, and then here I got a standard deviation of 2, whereas in graph B, my scores were spread between 1 through to 10, and my variation was 4. Okay, I hope you can now tell the relationship there, you know, between the spread of scores and standard deviation, just how to interpret all this information. Okay, the smaller the spread in scores, the smaller the standard deviation, and vice versa. If you enjoyed this video and found it helpful, please don't forget to hit the subscribe button before you go. And also check out our social media pages across all the platforms under Ask Cassie.